Okay, so we were doing moment of inertia of some symmetrical bodies. Okay, so okay, so now let us take the example of a cylinder. Okay, about its own axis. Okay, suppose a cylinder is rotating about its own axis. Okay, all right, the radius of the cylinder is r and length of the cylinder is L. Okay, so first let us take a disc, okay, obviously of radius r, okay, the same radius as that of the cylinder. Actually we are cutting a slice, okay, and that slice is a disc, right? Clear? Okay, now let us call the mass of this slice is dm. Okay, so the moment of inertia of this disc about this axis will be certain. You have already taught the moment of inertia of a disc, so it will be di will be half m r square, so half dm capital R square. So the entire cylinder can be thought of collection of such discs. Okay, so the entire the moment of inertia of the entire cylinder will just be the integral, right? So integral di will be half r square is constant, so integral dm. So total mass of the cylinder is capital M, so it will be I equals half m r square. Okay, now if we want to calculate the moment of inertia of this cylinder about an axis passing through its center of mass and perpendicular to its length. Okay, the axis is passing through the center of mass and perpendicular to its length. So how to calculate this? Again we have to consider a disc, a slice, okay, an elemental disc on the cylinder. Okay, so let us consider it like this. Okay, all right, clear? Okay, at a distance x, okay, fine. Now if we take this to be the diameter of the disc, okay, so about this diametrical axis, what is the moment of inertia of the disc? Suppose the mass is dm, okay, so about the diametrical axis it is 1/4 mr square, that is dm r square, right? So it is actually the moment of inertia of the diametrical axis. So it is the diameter is an axis passing through the center of mass of the disc. Now what will be the moment of inertia of this disc about this axis? We can use the parallel axis theorem. Okay, so using parallel axis theorem, what we can write? the moment of inertia of this disk di is equal to the moment of inertia about the diametrical axis, that is ICM plus m r squared, that is m a squared, the perpendicular distance between the parallel axis, that is x squared. Okay, fine. So now let us consider that the density of the cylinder is rho. Okay, so what is the volume of this elemental disk? It is pi r square h. Let this width of this disk is dx, so it will be pi r square h, the volume, right? So pi r square dx, capital R, r square dx. Okay, the volume into the density will be the mass dm. Okay, so here di can be written as, then let us integrate, 1 by 4 r square integral dm plus integral dmx square. Okay, so I will be, if I integrate all these the moment of inertia of this all these elemental disk, I'll get the moment of inertia of the entire cylinder about this axis, that is I. It is clearly, this is 1 by 4 capital M r square plus, now this would become pi r square dx rho into x square. Okay, fine. So I would become 1 by 4 m r square plus pi r square rho is a constant taken out of the integral, it is x square dx. Now this is origin, x equals 0. So this, the entire length is L, right? So it will be x equals minus L by 2 to x equals plus L by 2. So minus L by 2 to plus L by 2. So it will be I equals 1 by 4 m r square plus pi r square rho, this is x cubed by 3 minus L by 2 to plus L by 2. So it would become, okay, plus pi r square rho, this is L cube by 8 into 3, 24, the upper limit, minus the lower limit, it will be minus L cube by 8 by 3. So it is 2L cube minus minus plus, so it is 2L cube by 24, that is L cube by 12. Okay, so if I write it like this, m r square plus, let us write it like this, 1 by 12 pi r square L rho L square. Okay, so the volume into density, the total mass. Okay, so it will be 1 by 4 m r square plus 1 by 12 ml square. So let us take m common, r square by 4 plus L square by 12. Okay, so it is the moment of inertia of the cylinder, okay, about this axis. Fine. Now let us calculate the moment of inertia of a solid sphere. So let me complete it. So for a cylinder, I give you as a homework this thing. So I know the moment of inertia about this axis. This is actually passing through the center of mass, right? So if I ask you to calculate about this axis, you can calculate using the parallel axis theorem. Okay, fine. Again, the moment of inertia, you know about this axis. About this axis, this is passing through the center of mass, so it is ICM. So if I ask you to calculate the moment of inertia about this axis, that is I, okay, then you can calculate it using the parallel axis theorem. What is the distance then? L by 2. Okay, as simple as that. Use this thing plus ms square. So these two things, okay, you will try at home. Okay, fine. Now let us calculate the moment of inertia of a solid sphere. About a diametrical axis. Okay, so let us take a solid sphere like this. Okay, so let us calculate the moment of inertia about this diametrical axis. Okay, so first, again, let us consider a strip which will be a disc. Okay, like this. Okay, if I cut a slice from this solid sphere, you visualize, you try to imagine, it will become a disc. So what will be the moment of inertia of this disc? Okay, see, this is the radius of the sphere, call it capital R. Okay, now the radius of this disc is smaller, right? And let this distance is x. Okay, the width is dx, call it. Okay, so first the mass of this disc, dm, the volume is pi r square h, pi r square dx into density is rho, right? So it will be dm. Acha. Now what is r? Again, can you see this triangle now? You can see this triangle. This is r, this is capital R, this is x. Clear? Okay, so you can tell that x square is rather r square is capital R square minus x square, right, from Pythagoras. Okay, so now tell me what is the moment of inertia of this disc about this axis. It is clearly half m r square, right? So it will be di is half dm small r square. Okay, so the entire disc can be considered as a collection of such discs, isn't it? So if I add them all, integrate them all, I'll get the total moment of inertia of the whole sphere. Okay, so let us write di as half pi r square dx rho into r square minus x square. Okay, oh now let it write r square, so it will be I r4 half pi rho r4 dx. So r4 will be, tell me, half pi rho r square minus x square whole square dx. So if I integrate, I get, acha, let me write it like this: r4 minus 2r square x square plus x4 dx. So if I integrate, di will be half pi rho r4 integral dx minus 2r square integral x square dx plus x4 integral x4 dx. Now x will be from 0 to r. Okay, clear? From 0 to r. Okay, so it will be 0 to r, 0 to r, 0 to r. So I is half pi rho, it will be r4 into r, 2r square into r cube by 3, because it is x cube by 3, upper limit r cube by 3 minus lower limit 0, so I am not putting 0 here. Also r minus 0 is r, and this is x5 by 5, that is r5 by 5 minus lower limit 0, I am not writing it. So what I am getting is half pi rho r5 in all terms. So r5, let us take it common, 1 minus 2 by 3 plus 1 by 5. So it will be I equals half pi rho r to the power 5. It will be 6 by 5 minus 2 by 3. So it will be half pi rho r to the power 5. It is 15. 18 minus 10. So it is 8 by 15, right? So half pi rho r to the power 5 into 8 by 15. So it is 4. So I am getting 4 by 15 pi rho r to the power 5. So let us write it like this: 1 by 5 4/3 pi r cube rho. Okay, into r square. I've missed a 2 somewhere, I think. Oh yes. Oh yes. I have taken x, the limit of x from 0 to r. Okay. But I should have taken it from minus r to plus r, na, for the whole sphere. Okay. So otherwise just 0 to r I have taken, na. So I have to multiply it by 2. Because from 0 to r I am taking half of the sphere. So to get the full sphere, I will just multiply it by 2. Okay, fine. So let me multiply it by 2. Okay, while integrating I am multiplying it by 2. Okay, so here 2 and 2 cancels, so no 2 will be, no half will be there. Okay, so it will be just 8 by 15. Okay, So we'll write it as 2 by 5, 4 by 3, so 8 by 15. Now you say 4/3 pi r cube is the volume of the cube into density. Volume into density is mass. So it is the total mass of the sphere. So it is 2 by 5 mr square. Okay. So I is 2 by 5 mr square. The moment of inertia of the solid sphere about a diametrical axis. Okay. So total mass of the sphere I have taken as m. Okay. And density rho. Okay. Now if I take a tangent, a tangential axis like this. Okay. So about a diameter already I have found. Now about a diameter, this is actually passing through the center of mass. So ICM. Okay. So if I know ICM, that about the diametrical axis, then by parallel axis theorem I will calculate this I. So I will be ICM plus mr square. As simple as that. So it will be 2 by 5 mr square plus mr square, that is 7 by 5 mr square. Okay. So now let us calculate the moment of inertia of a thin spherical shell. Okay. So this is a thin spherical shell. Okay. The inside the shell it is hollow and the surface is very thin. Okay, fine. So it's basically a hollow sphere, right? So now let us consider a strip like this. Okay. Now you have to imagine, visualize that if you cut a strip like this from the shell, you will get a ring, right? Clear? Okay. The radius of the ring will be, say, r. Okay. Now if you we will calculate the moment of inertia about a diametrical axis. Okay. Okay. So this is the center. Okay. Now join it. This is the radius of the shell, capital R. Alright. So this angle is theta. Okay, fine. Now if you consider this much, okay, so this is d theta, right? Now this length is r d theta, the arc length. Okay, fine. Now say mass per unit area. is sigma. Okay, so what is the mass of this ring, this strip? Actually, the surface area will be 2 pi rh, that is 2 pi r, and h is r d theta, right? 2 pi rh, the surface area, the curved surface area of a cylinder basically. Okay, this is basically a cylinder, the curved surface area you have to consider, right? This is the curved surface area. Okay, you have to imagine it three-dimensionally. Okay, into sigma. Okay, per unit area it is sigma, so the area of this the mass of this area is the area into sigma. Okay, so fine. Now say the moment of inertia of this ring about such axis passing through its center of mass will be di is mr square, that is dm into r square, right? Now put dm here. So let's say the total mass is m. Okay, so di is 2 pi r d theta into sigma into r square. Okay, so it is di 2 pi sigma r into r cube d theta. Alright, now from this triangle, you say from this triangle, okay, what is r? Okay, cos theta, sin theta is smaller by capital R, right? So r will be r sin theta. So you will get di as 2 pi sigma r into r cube sin cube theta d theta. Okay, now you can consider such rings, okay, throughout the sphere, spherical shell. Okay, and if you add all moments of inertia of these rings, you will get the total moment of inertia of the shell. Okay, so you have to basically integrate it. Okay, so if you put integral on both sides, you'll get this. Okay, so I is 2 pi sigma r to the power 4 sin cube theta d theta. Acha, theta will be from 0 to pi. Okay, from 0 to pi. Okay, if theta goes from 0 to pi, you go from this point to this point. So you are adding all these rings from this point to all this ring you are adding, right? Clear up to this point. Okay, so the whole shell is done. Okay, so it is I equals 2 pi sigma to the power 4. Now if you multiply the numerator and denominator by 4, you get this. Okay, 4 sin cube theta. Now from trigonometry, you know, by 2 0 to pi, you know it is 3 sin theta minus sin 3 theta. Okay, so what do you get? You get 3 sin theta d theta from 0 to pi and sin 3 theta from 0 to pi. So now you can easily calculate. Okay, into 3, this is minus cos theta from 0 to pi, and this is minus cos 3 theta by 3 from 0 to pi. Okay, so it will be 3 by 2 pi sigma to the power 4 minus cos pi upper limit minus minus plus cos 0 lower limit, and here it will be minus pi sigma to the power 4 by 2. 2 into 3 make it 6 na. So it is minus cos 3 pi minus minus plus cos 0. Okay, so it is 3 by 2 pi sigma to the power 4. This is minus minus plus 1 it's 2, and here it is pi sigma to the power 4 by 6. Cos 3 pi is minus 1 minus minus plus 1 plus 1 into 2, so it's 3. So you get 2 and 2 gone. Pi sigma to the power 4, 3 minus 1 by 3, 8 by 3 pi sigma r to the power 4. So it is I equals, so it can be written as this: 2 by 3 into 4 pi r square sigma into r square, right? You can manipulate. So 4 pi r square is the surface area of the spherical shell, into sigma, mass per unit area. So you get the total mass m. Okay, total mass m. Okay, fine. M is basically this 4 pi r square into sigma. Okay, so this is m, so it becomes 2 by 3 m r square. Okay, now about a tangential axis. Just like in the case of a solid sphere, you can find the moment of inertia using the parallel axis theorem. So this is ICM, the radius is r, so I is ICM plus m r square. So already you know ICM, the diametrical axis formula, 2 by 3 m r square plus m r square. It becomes 5 by 3 m r square. Alright, clear? Fine. So now let us calculate the moment of inertia of a cone about its axis of symmetry. So consider a cone here. So about this axis you have to find the moment of inertia, right? So first you consider a solid cone. This is a solid cone, okay? Acha. You consider a strip which is a disc basically, okay? Okay, fine. Now you tell me one thing. Say the radius of the cone is r and height is h. So the radius of this disc, call it x, and the height from here to here, call it y. Okay, so this width is dy, this width will be dy. Alright, so mass per unit so density is rho. So mass of this disk will be volume into density. So volume is pi x square dy, pi r square h, into density rho. Alright, so the moment of inertia of this disk will be di is half mr square, that is half dm into x square. So it will be half pi x square dy rho into x square. So it will be, so if we have to calculate the total moment of inertia, we must integrate it. So half pi rho, it will be integral x4 dy, right? Okay, now you see from these two triangles, a small triangle and a big triangle. Okay, these two triangles are similar as they have a common angle. These two angles are equals and both of them are 90 degrees. Okay, so this is a similar triangle. So corresponding sides, the ratio of corresponding sides will be the same, that is y by h will be x by r. Okay, so it will be y is x by r into h, so dy is h by r into dx. So it will be I equals half pi rho, so h by r x4 dx. Now the limit of x, here it is 0 and here it is r, so from 0 to capital R. So it will be x5 by 5, that is r5 by 5 minus lower limit 0, I am not writing it. So it is 1 by 10 pi rho h r4. So it is 3 by 10 1/3 pi r square h. Okay, into rho into r square. So volume into, this is the volume, the entire thing is the volume of this cone, into density the mass. Okay, so total mass is m. Alright, so we'll get I equals 3 by 10 mr square. Okay, so now if I want to calculate the moment of inertia of the cone, about this axis. Okay, how to calculate it? We already know we have to take a strip like this, which is a disc, a slice. Okay, so this is y and this is dy. So what we will do, see, if we think of a diametrical axis through this disc, we already know what is the moment of inertia, 1 by 4 mr square. Okay, now if I know this, then I, by parallel axis theorem, because it is the center of mass of the disc through which it is passing, so if I know this, then I can use the parallel axis theorem to find the moment of inertia of this disc about this axis, right? So di will be one by 4 dm x square plus dm into y square. Alright, y is the distance, perpendicular distance between the parallel axes. So it will be 1 by 4 rho into pi x square dy into x square plus rho into pi x square dy into y square. Okay, now so integral di will be 1 by 4 pi rho, it is x4 di dy, and this is pi rho x square y square dy. Okay, now how to do it? We already know that from the similar triangle, what we can tell, as this is h, we have already shown this thing, that y by h is x by r. So y is x h by r, so dy is h by r dx. So here I will be 1 by 4 pi rho h by r x4 dx plus pi rho x square h square by r square x square h by r dx. So it is pi rho h by 4r x4 dx from 0 to r plus pi rho h cube by r cube x4 dx 0 to r. So it will be pi rho h by 4r into r5 by 5 minus 0 lower limit. So it is pi rho h cube by r cube. It is becoming also r5 by 5. So ultimately what you are getting is, it is 1 by 20 pi rho h r4 plus 1 by 5 pi rho h cube r square. So it is, you can do it like this: 3 by 20 1/3 pi r square h rho into r square plus, this is also 3 by 5 1/3 pi r square h rho into h square. So it is 3 by 20 mr square plus 3 by 5 mh square. Okay, so it will be 3 by 5 m r square by 4 plus h square. Okay, so if I can do this now, if they ask you find the moment of inertia about an axis through the center of mass of this cone like this, okay, you can find it by the parallel axis theorem, because you know the moment of inertia I about this axis. Okay, now you know the perpendicular distance. The center of mass for a solid cone, it lies at a height of h by 4 from base. Okay, all right. Alright, so this thing is 3h by 4. So I is ICM plus m into 3h by 4 square. So as you know I, you can find ICM as I minus 9 mh square by 16. Okay, so calculate yourself at home. Okay, fine. A rectangular lamina. Okay, suppose a rectangular lamina is there, okay, of length L and breadth B, call it B and call it L. Okay, now let us consider an axis like this. Okay, then we can think of a strip. Okay, like this. Now this is a rod. Okay, a rod of length B. Okay, so the moment of inertia, suppose the mass of this rod is dm, so the moment of inertia will be di, will be 1 by 12 dm into b square is passing through the midpoint, the center of this rod. Okay, so in order to calculate for the whole lamina, we can consider such rods. Okay, so we must integrate it. Okay, so I will be it is 1 by 12 b square integral dm. So I will be 1 by 12 mb square. Okay, now if the axis is like this, okay, then you will consider rods like this. Okay, so in this case, so here the axis was parallel to length and here the axis is parallel to breadth. Okay, so here you will consider it like this. Di is 1 by 12 passing through the midpoint of the rod, dm l square. L is the length of this rod. Alright, clear? And for the whole lamina you need to integrate it. So you will get 1 by 12 ml square. Okay, so if they ask you what about an axis passing through the center and perpendicular to plane, can you find it? Of course, an axis is like this, passing through the center, okay, and perpendicular to the plane. Okay, so it is pointing outside the screen actually. Alright, clear? It is like this. If you draw it like this, it will be easier for you to understand. The axis is like this. Okay, fine, clear? So already you have done these two things. This one call it ix and this one call it iy. Okay, now this axis will obviously be the iz, isn't it? So iz will be ix plus iy, perpendicular axis theorem. So iz will be 1 by 12 ml square plus mb square. So 1 by 12 common, m l square plus b square. Okay, so about this axis you can find. Okay, so if they ask you what is the moment of inertia about a diagonal, okay, acha, for a square what it will be? L equals b, so iz becomes 2l square, that is 1 by 6 ml square. Okay, so if they ask you now what about a diagonal? Okay, but the diagonals are not perpendicular to each other, so it will not be for rectangle, it will be as for a square. For a square, obviously the diagonals are perpendicular to each other. Okay, so it is symmetric, so for both of them it will be I, and obviously you know Iz passing through the point of intersection of the perpendicular axis. Again you can use the perpendicular axis theorem and you get I plus I is Iz, so 2I is 1 by 6 ml square, so about a diagonal it will be 1 by 12 ml square again. Okay, where L is the side length. Clear? Okay, about a diagonal. Fine. Now let us do the moment of inertia for a triangular lamina. So, in order to calculate the moment of inertia of the triangular lamina, let us have a triangle like this. Okay, so this is the height. Okay, now suppose let us calculate the moment of inertia about one side as axis. Okay, suppose this is the axis. Okay. Fine, so the base is B and height is H. Okay, so first let us consider a strip. Okay, so this is a rectangular lamina. Okay, a rectangular strip. So let me draw H here, height. Okay, so let me call this much height is Y and the rest of it is H minus Y, right? Okay, now what will be the moment of inertia of this strip about this axis? Okay, suppose the mass is dm. Okay, fine, so the let me call the width is dy, right? Okay, so this axis is parallel to length. Okay, so it will be 1 by 12 m, 1 by 12 m, that is dm, into breadth square, that is dy square. Okay, we did it earlier. Okay, yes, all right. So now if I know the moment of inertia of this rectangular lamina about this axis, then by parallel axis theorem I can calculate the moment of inertia of this yellow lamina about this axis. So it will be plus dm into h minus y square. Okay, the perpendicular distance between these two axes, h minus y. Alright, fine. So you see, so this is di. Now dm is small and dy is small, so dy square is even small. So basically this product is a third order smallness, so we can safely neglect it. So ignoring it, the moment of inertia is becoming dm into h minus y square. Okay, now suppose the mass per unit area is sigma. Okay, now what is the area of this rectangular strip? Okay, let us call it x. Okay, so it will be 2x dy. Okay, the area is 2x dy. Okay, the length into breadth. Alright, so it is 2x dy, the area, into mass per unit area sigma. So this is the mass dm. Alright, so I can write it as 2x dy into sigma into h minus y square. So now from this true similar triangle, the smaller one and the larger one, we can write the ratio of corresponding sides be equal. So y by h is equal to x by b by 2. Okay, this b by 2 it is. Alright, so it is 2x by b. So x will be b by 2h into y. Okay, now put it here. So 2b by 2h into y dy into sigma h minus y square. So let us integrate. So it will be b sigma by h integral y h minus y square dy. Now y will be from 0 to h. Here it is 0 up to h. Clear? So you see we get I is b sigma by h. It is integral 0 to h y h square minus 2hy plus y square dy. So I will be b sigma by h. It will be h square y dy from 0 to h minus 2h y square dy from 0 to h, and finally y cube dy 0 to h. So we get b sigma by h square into y square by 2, that is h square by 2 minus 0, I am ignoring the lower limit. So it is 2h. It is y cube by 3, that is h cube by 3 minus 0, plus it is y4 by 4, that is h4 by 4. So it will be I is b sigma h4 by h half minus 2 by 3 plus 1 by 4. So it is B sigma h cube 3 by 4 minus 2 by 3. So it will be 12, 9 minus 8, isn't it? So it is 1 by 12 B sigma h cube. So I can write it like this: 1 by 6 half B h sigma into h square. Now total mass of this lamina will be m. Okay, let the total mass of this lamina is m. Okay, so m is certainly the total area into mass per unit area sigma. Okay, so m will be certainly half b sigma, half bh, half into base into height, the total area into sigma. Okay, so it will be 1 by 6 mh square. Okay, the moment of inertia. Now we can calculate the moment of inertia of this triangular lamina about several other axes like this. Suppose about this axis, what it will be, I. Okay, and first let us consider this axis ICM. Okay, this is the center of mass. Okay, the center of mass, we know, if we consider it as the median. Okay, so center of mass actually, this is h by 3, this is 2h by 3, we know this. Okay, so we have already calculated this I. Okay, call it I1 then. So I will be ICM plus mh by 3 square. So I is 1 by 6 mh square. So it is ICM plus 1 by 9 mh square. So ICM will be mh square by 3. So it will be half minus 1 by 3. So it is 6, 3 minus 2, 1 by 6. So it is mh square by 18. Okay, so now you can again use parallel axis theorem. We have used here the parallel axis theorem. Okay, so again we can use the parallel axis theorem to find I1. So I1 will be ICM plus m 2h by 3 square. So it will be like mh square by 18 plus m 4h square by 9. Okay, so it will be mh square by 9. So it will be half plus 4. So it is 9 by 2. So it is I1 is mh square by 2. Okay, fine. So you have calculated like this. Okay, so now it's your homework to make a table, okay, of moment of inertia of different objects about different axes. ওকে, আমি যেগুলো করলাম সেগুলো তো করবেই, তার সাথে তোমরা আরও বাড়িতে নতুন কিছু ট্রাই করতে পারো কয়েকটা, যেমন হলো সিলিন্ডার, হলো কোন। ওকে, ইউ ক্যান ট্রাই দিস থিংস অ্যাট হোম। ওকে, you can do this as homework. Hollow cylinder. Okay, about the axis already I have told for the solid cylinder. Then hollow cone. Okay, you can do this. Okay, already the axis I have told. Okay, fine. Okay.